In section 10.3, we found the values of some infinite series because we could, namely geometric and telescoping series, for which we could find the sequence of partial sums and we could evaluate them and actually get a number. Unfortunately, that's not something we're going to be able to continue because it's difficult or impossible to find an explicit formula for the sequence of partial sums for most infinite series. Most infinite series, we're not going to be able to find an exact value. It just won't happen. So we enjoy the geometric series and the telescoping series because they're the two series that we really can find the sum for quickly and easily. But the vast majority of infinite sums, we're not going to be able to find a value of. So if we can't find the value, then what are we going to do? And the answer is we're going to ask whether it does converge or does it diverge. So instead of looking for the sum of the series, we're just going to ask, would it sum to something if I could figure out what it was? All right. So we're not going to be able to find the number. We're just going to ask, should it go to a number or not? Right. So we're no longer going to be able to find that specific value. And that's basically what we're going to do for the rest of this chapter. We're going to keep looking at sums or series and sums and figure out whether or not it would converge or whether it would diverge. But we're not going to find the actual evaluation point of convergence because you can't the vast majority of the time. All right. So first things first, we're going to talk about that divergence test. So the divergence test says that if the limit, well, if the series converges, then the limit of the sequence values is 0. Equivalently, if the limit is not 0, then the series diverges. Okay, so what they're saying is, look, if you're going to make it so that an infinite series converges, then it has to be that the values are shrinking for the sequence. Otherwise, you'd be going to infinity, right? And that's what this is saying. So if you're not going to 0, let's say you were going to, 0.2. Adding up infinitely many 0.2s is going to make infinity, right? Adding infinitely many 0.1s is going to make infinity. So adding up infinitely many of anything that is not 0 will automatically make it infinity, period. However, if the sequence goes 0, that does not necessarily mean that the series converges. It's a necessary condition, but it's not a sufficient condition. So let me just say this. So it's necessary that the limit as k goes to infinity of a sub k, the sequence, is 0, but not sufficient. It's not enough. So this is how we're going to test for divergence. The divergence test basically says, hey, figure out if it's not going to 0. Because if it's not going to 0, then you're done and the series diverges. If it is going to 0, well, then that's what the rest of the sections in this chapter are going to be about, because that's not going to be enough, right? That'll just be the starter of what you need. So then the question is it going to 0 fast enough, quickly enough that it will converge to a number or not? Well, more on that later. All right, so let's figure out whether these series diverges or state that the divergence test is inconclusive. All right, so you might be thinking, what does that mean? Well, okay, if the limit is not 0, right here, then the series diverges, right? So that's the divergence test. The divergence test is inconclusive if the limit is 0. So over here, if this is true, then it will be inconclusive because, I guess I could put it here. Inconclusive because it's necessary, but it's not sufficient. It's not enough. So we don't know enough to prove that it converges. It might still diverge, right? You're thinking, well, that means that this divergence test isn't the only type of way to prove divergence. That is correct. There will be lots of different tests. That's what chapter 10 is about. All right, so let's start with this one. So my infinite series starts at 0, goes to infinity, is of this sequence. So I'm going to add the terms of this sequence. So I need to think about the limit as n goes to infinity of that sequence. 4n squared minus n cubed over 10 plus 2n cubed. All right. Well, that's infinity over infinity. Remember infinity over infinity? Because I do. Right? So that means that you can use L'Hopital's rule and find the limit of the next bit. So take the derivative of the numerator, take the derivative of the denominator, and they will be equivalent. They're not equal technically. It's equivalency with L'Hopital's rule. So that would be 8n minus 3n squared over 6n squared. It's still infinity over infinity. So therefore I would do another L'Hopital's rule. And it would be the limit as n goes to infinity of 8 minus 6n over 12n. That's still infinity over infinity. This is still infinity over infinity. Technically, it was the beginning part that was infinity over infinity. So this one is infinity over infinity. So that means I do another L'Hopital's rule. And that would be the limit as n goes to infinity of the derivative of the numerator, which is negative 6, over the derivative of the denominator, which is 12. And now it's no longer infinity over infinity. That is negative 1/2. And you know what negative 1/2 is not? It's not 0. Therefore, this series diverges by the divergence test. Right there. It's got to go to 0. If it doesn't go to 0, then you are diverging. If it does go to 0, you may be converging, you may be diverging. We don't know. It's inconclusive. All right, next one. All right, well, I'm going to take the limit. I'll do it in a different color just to make it clear. So limit as k this time goes to infinity of k over k plus 1. That's infinity over infinity. So that would be equal to the limit as k goes to infinity by L'Hopital's rule. Got to put the little L'Hopital over it because they're not technically equal. They're equivalent based on L'Hopital's rule, but they're not the same. So a little L'Hopital over the equal sign. And then it's the limit of 1 over 1, which is 1. Hey, you know what 1 isn't? 1 is not 0. If you're adding up infinitely many 1s, you're going to get infinity. It's going to diverge. So therefore, the series diverges by the divergence test. There we go. Okay, now what about 1 over k? Okay, so the limit as k goes to infinity of 1 over k would be 1 over infinity, which is 0. We learned that back in chapter 2, heck, a long time ago in Calc 1, that the limit of 1 over infinity is 0, right? Ooh, I guess I should have just put that there. Okay, so that means it converges, right? Wrong. We don't know. This may converge, it may diverge. We don't know. So the test, divergence test, is inconclusive. Same thing over here. The limit as k goes to infinity of 1 over k cubed is 1 over infinity cubed, which is 0. Sorry, I wrote that wrong. So if you want to make a little note, it's 1 over infinity cubed, which is 1 over infinity, therefore it's 0. Again, we learned a long time ago that the limit, well, we learned this one right here. The limit as k goes to infinity of 1 over k is 0. We learned that back in chapter 2. So that's an old one. All right, these bottom two, you might be thinking, oh, well, they both converge. Actually, it's not true. It's inconclusive. So the divergence test only tests for divergence by taking the limit. So the divergence test is inconclusive for both of these because the limit is 0. The series may converge and may diverge. We don't know, right? Just having the limit of the sequence go to 0 is necessary, but it's not enough, right? It's not enough to know whether these sequences or these series converge or diverge. As a matter of fact, that one diverges and that one converges. Huh? But you would never know it from this test. This test isn't enough to give it to you. So you're going to need another test, right? So we will need more tests, and you'll be getting a whole bunch of them. The ratio test, the comparison test, the root test, you're going to have a whole bunch of tests in this chapter with which to check these series and see whether they converge or diverge.